Alright, so the goal of this video is to take a look at the graphs of higher degree polynomials and just all polynomials in general. So we know about a couple of them already, and we're going to take a look at the rest of them and see how they, what kind of similarities they have, and how we can kind of get a picture in our head of what the graph's going to look like without knowing a whole lot about it ahead of time. So to start off with, we have a definition. This is talking about the degree of a polynomial. So when we're talking about the degree of a polynomial, if it's in a standard form where all of the parts are put together, we're going to say if you take a look at the highest exponent of all of the variables in that polynomial, that's going to tell you about the degree of the polynomial. Usually if it's in standard form, that number is in the first position, but if it's all mixed up, you might have to fix it yourself. Okay? If we already have the expression factored and it's broken down into pieces, the degree is going to be the number of factors counting all of the duplicates. So for example, if I had something that looked like, moving stuff around, okay, if I had something that looked like an x plus 1, okay, and an x minus 3 and an x plus 1 again, right, I would say that this is a degree 3 polynomial because I have 3 parts. It doesn't matter that this x plus 1 is going to give me a couple of the same answer when I solve them. It just really matters that there are 3 answers. We're counting all of the duplicates as a part of our answers. Okay, even if I had, like, for example, an x cubed at the beginning of this, I would actually call this one a degree 6, because this cubed actually means x times x times x, and then I have these additional 3 here, so I actually have 6 of them, right? So we're going to take a look at a couple of examples, and the first thing we're going to do is just determine what is the degree of each of these polynomials. Okay, so if you take a look, I'm giving you 2 expressions in number 1 and number 2, where we're just being asked the degree of the polynomial, but they are already put together for us. It's one long expression. Okay, g of x, we're just going to look at this and say if I'm scanning all of these x coordinates, okay, I'm sorry, these x variables, okay, it looks like there's 3 of them. Remember that x has an x to the first power. I'd look at them and I'd say the highest exponent is 6. Okay, so this is a degree 6 polynomial. And that's all this is about. Okay. Second one, again, just be careful. I did it over here. If I ask what's the degree of 5x, there is an exponent here. I would say it is a degree 1 polynomial. Okay. So let's take a look at these ones that are in factored form. Right. I would actually take a look at this and I would say 1, 2, 3, and then x minus 2 cubed actually means x minus 2, x minus 2, x minus 2. So this one right here is actually giving me 3 unique additional zeros. So let's write that as what they're giving us and not counting. Okay, so I'll call this 1. This is contributing 1. This is contributing 1. This is contributing 3. So if I counted these up, 1, 2, 3, 6. This is also a degree 6 polynomial. Okay, so now let's do the same thing with this next one. I'm claiming that this is also a degree 6 polynomial. It looks very different, okay, but here's the way it's going to work. I'm getting 2 different factors, 3x minus 5 and a 3x minus 5. I'm getting an x plus 1 from this last one, so that's only one of them. There's no exponent out here. Okay, and I'm getting 3 unique factors, well, 3 factors from this one right here. So this is really, okay, 6 different pieces, right? 3 different x's, 2 different 3x minus 5s, and an x plus 1. This is also a degree 6 polynomial. Okay, so when you're looking at these problems, it's really just a matter of taking a look at either the highest exponent in factored form, okay, or I'm sorry, in standard form, or we're taking a look at how many factors we have, counting all of the duplicates if it's in a form like you see for problem number 3 and problem number 4. Okay, so here's the question: why do we care about this? So we care about the degree of the polynomial because it's going to tell us a lot about what the graph looks like. So it tells us really 2 distinct things. So these first 2 are giving you what the degree tells us about what we call end behavior, right? And what the end behavior is describing for us in what direction the ends of the graph are going to go. So what I'm claiming here is that if the degree of the polynomial is even, like for example in our last problem we had a degree 6 polynomial, if you have a degree 6 polynomial, I'm claiming that both of the ends of the graph will be traveling in the same direction. So they'll either both be going up, which if you notice right here I'm calling up slash up, okay, or we're doing down slash down. So when I say up slash up, what I'm referring to is the left side will be up slash the right side will be up, or the left side will be down slash the right side will be down. Okay, if the degree of the polynomial is odd, okay, like for example if we have a degree 1 polynomial or a degree 5 polynomial or a degree 23 polynomial, okay, I'm claiming that the ends of the polynomial will always travel in opposite directions. So down slash up, means that on the left-hand side it's traveling down, on the right-hand side it's traveling up. Okay, and then up slash down just means the opposite. Okay, on the left-hand side it's going up, on the right-hand side it's going down. So that's one thing it tells us. It's going to tell us about the direction of the ends of the graph, which again you're going to hear me refer to as end behavior. Okay, and it also the degree also is going to tell us at most how many times the graph is going to turn as we're connecting together those two ends. Okay, so for example, a degree 6 polynomial could only turn at most 5 times. That's what degree minus 1 means. If I have a degree 20 polynomial, it's possible that it could turn at most 19 times, right? So it's always one less than the degree of the polynomial, okay? So what we're going to do now is we're just going to look at one of those polynomials, and we're going to look at it the old-fashioned way first, and that is just using a table of values, plugging in, and graphing and seeing what it looks like. So in this example here, I created a bunch of x values. We're going to graph the parent function of y equals x cubed and see what it looks like. So if I plug in x cubed, a negative 2 in for x cubed, okay, what I'm going to get out of this is negative 2 times negative 2 times negative 2, which is negative 8. Okay, when I plug in a negative 1, I get negative 1 times negative 1 times negative 1, which is negative 1. Okay, 0 cubed is 0 times 0 times 0. Okay, 1 cubed is 1, and 2 cubed is 8. Okay, so if I graph these points, here's the parent function, okay, for a cubic. It looks like I have a, let me slide down a little bit. Okay, it looks like I have a negative 2, 8, which is going to be way down here. Okay, there. Okay, if I have a negative 1, negative 1, 0, 0, okay, 1, 1, okay, and 2 all the way up to 8. Okay, so if you notice what happens here is this thing travels pretty straight up, okay, and then it makes a sharp turn, okay, and starts heading kind of in a straight line, and then it makes another pretty sharp turn and starts heading up again. Okay, so if I notice, I'm going to describe two things for you that are happening. The first is it's turning twice, right? Highest exponent of 3 means that it can turn at most 3 minus 1 times, which is twice. So this graph is turning right here, okay, and heading that way. And then it's kind of moving up, and then it's turning again right here, okay, as it heads more straight up. So it's kind of going from the left side, it's heading up really fast, and then it turns, and then it's heading up again, and it turns up straight again. Okay, so we get 2 turns. That makes sense as far as what we just described. It's turning at most 2 times. Okay, the other thing that's happening is I can describe the behavior of the endpoints, and I can say this particular one is an odd function. Okay, and what we just described on the last slide is we said odd functions should go either down up or up down. And in this case, it looks like we have a down-up situation. Okay, so if you take a look at my endpoints, the left-hand endpoint is down, okay, and my right-hand endpoint is up. So I would describe this as a down-up function with 2 different turns. Okay, so on the next slide, I'm just asking about those things. Okay, so again, I already pre-graphed this one. Let me just draw a picture. Okay, if I gave you this picture, or anything that looks like it, even if you didn't know it was a cubic function, and I asked you to describe the end behavior of this graph, you're going to say it's down on the left, okay, and up on the right, which we just write as down, up. Okay, how many turning points does it have? I see it, again, turning when it's getting to this negative 1, 1, and then it's turning again to head straight up, so I would say it has 2 turning points, okay, and that's all we're looking for. Okay, so there's one more thing that we have to talk about when we are describing the graph by using the degree and some basic information about the polynomial, and that is, well, how do we know if it's up, up, or down, down when we're talking about an even function? How do we know whether it's down, up, or up, down when we're talking about an odd function? Okay, let me close my parenthesis there. Okay, so what's going to tell us about which of those two we should use is the lead coefficient's sign. So if it's positive, we're going to end up with an up, up for an even function. If it's negative, we're going to end up with a down, down. And guess what? You already know about this. Okay, if I were to draw the parent function for y equals x squared, okay, this is an even function. We know that the parent function points up, up. If I put a negative sign in front of that, so now it's got a negative lead coefficient, it would turn to down, down. Okay, we also just saw when we talked about cubic functions, that the parent function for that kind of looks like this, where it curves and then heads straight up. Okay, if you notice, it's down on the left, up on the right. That's the parent function when it's positive. So guess what do you think is going to happen when I put a negative sign in front of the lead coefficient? Is it's just going to switch the sides. It's going to be up on the left, okay, and it's going to go down on the right, and it's going to look like that instead. Okay, so it's just this idea of on which side are the endpoints going up or down. That lead coefficient is going to tell us. Okay, so to wrap it up, what we're going to look at is first just looking at some polynomials, and we're going to describe the end behavior using that lead coefficient. So the way I'm going to look at this one is I'm going to say, okay, even function because I have a degree 2 polynomial. Because it's even, I know that the end behavior is either up, up, or down, down. Okay. The way I'm going to determine which one of those to use is I'm going to look at this number, this right here, right? The lead coefficient has a negative sign, and so I'm going to describe this as down, down. Okay. If that lead coefficient was a positive number, I would describe it as up, up. Okay. So for this polynomial, if they ask me to sketch a possible graph, there's lots of different possibilities, but one possibility is going to be, I just know that it's going to be some kind of upside down parabola, right? It's got one turning point right here at the vertex, and it heads right back down, okay? 6th degree polynomial, okay? It has a lead coefficient of 3, which is positive. So again, any time we have an even coefficient, I know I'm going to have an up, up, or a down, down. The positive 3 is telling me that the correct answer here is up, up. So I know it's going to kind of look like this, the end behavior. Okay, because it's a degree 6, between these 2 points, it's allowed to turn at most 5 times to connect these together. So I could come down, and I could turn, that's once, turn, that's twice, okay, turn, that's 3 times, and then connect. I didn't go a full 5, but I don't have to. I'm just allowed to stop. I can't go any higher than 5. So that is a perfectly good sketch. Now, you might have something that looks like pretty much like a parabola, right? And this would be a perfectly good sketch. It's up, up, and it has 2 turns, which is not as many as 5. It could be up, up, like this, okay? And it could have the full 5. 1, 2, 3, 4, 5, and it might look like that. And that could be a possible degree 5 or degree 6 polynomial as well. They are all good answers. There is not one unique graph for a degree 6. Okay, so when I come down to the next group, number 3 is in factored form. So again, I got to be careful when I look at factored form. I'm going to look at this and I'm going to say 1 factor, 3 more of them. So now I'm up to 4, and there's a 5th one. So this is a degree 5 polynomial, and it has a negative lead coefficient. This 9 is negative 9, right? So I'm going to say this is remember the original cubic function was down on the left, up on the right. The negative is going to switch those. So it's going to go like up on the left and down on the right, okay? And then because it's a degree 5, I can connect together these endpoints, or these end lines, with at most 4 turns. So I could come down and say there's 1, 2, 3, 4. So something like that could be an example of a degree 5 polynomials graph. It's down up, or it's up down in this case, okay, and it's got 4 zeros. Okay, so last problem, and then we just got to look at 2 quick graphs just to do the same thing the other way. Excuse me. A degree 5 polynomial, positive now. So the only difference is that it's going to be up on the right, it's going to be down on the left. And in this case, instead of maybe having all 4 of the possible turns, maybe it's only got 1, 2 turns. And that's an entirely good graph, right? So there's lots of different possibilities, okay? So to finish up, we're going to just look at the graph and just do the opposite. So if I'm giving you this particular problem, okay, I'm saying, here's a graph. What is the least degree of the polynomial, and what is the sign of the coefficient, right? So I'm going to look at this, and I'm going to say, well, it's going down on the left, and it's going up on the right. Okay, down and up means that it's definitely an odd degree, right? Even degrees travel the same direction. These ones are heading in opposite directions. When the down is on the left and the up is on the right, I know it's got a positive lead coefficient. So I can say definitely a positive lead coefficient. Okay. And then they're saying, what is the polynomial of least degree? So I'm going to count how many times does this graph turn. Well, it looks like it turns right here at 3, 2, and it starts heading down. And then it turns again at negative 1, 3, and starts heading up. And it turns again at 2, 1, and again at 4, negative 1. So that's got 4 turns. If something's got 4 turns, the least degree that it could have is 5. Right? It could be maybe a 7 or a 9 or an 11, we don't know. But the smallest degree that it could possibly be is 1 more than the number of turns that we see. So we're saying that this is at least degree 5. Okay, and that's the best we can say. We don't know if it's a 5 or a 7 or not. Okay, so the second one's the same thing, but again, I'd say in this case, it's traveling up, up. Okay, so those endpoints are telling me that again I have a positive, okay, lead coefficient. And if I'm looking at the turns to figure out the least degree, I'd say it's turning in this case once, twice, 3 times, which means it's at least, okay, degree 4, right? Because if I have 3 turning points, it will be at least degree 4. Okay, so we have a lot of different information about the graphs just by looking at the exponents and looking at the lead coefficients. We can talk about end behavior. We can talk about turning points. Okay, and we can talk about a lot of the little details that are going to go into these problems. So we're going to definitely do more with this and get a lot more precise, but this is a good starting point for graphing.